So we have XS measurable space, mu signed measure, and then we could write X equals A union B, A positive set, B negative set, A intersection B empty. So this is called the Hahn decomposition. Then we define mu plus of E equals mu of E intersection A, and mu minus of E equals mu of E intersection B with a minus sign because it has to, and then mu plus minus measures at least one finite, and then you have mu equals mu plus minus mu minus, and this is called the Jordan decomposition. So the Hahn decomposition may not be unique, but the Jordan decomposition is unique, and we saw examples of these things. Okay, so now we say, so definition, mu plus is called the upper variation of mu. Mu minus is called the lower variation of mu, and mod mu equals mu plus mu minus is called the total variation of mu. So then we can also define, so definition, a complex measure is a set function mu defined on S and which can be written as mu equals mu1 plus I times mu2, where I is a root of minus 1. So mu equals I minus mu2, mu1, mu2 signed measures. Okay, so this is called a complex measure. Okay. So now proposition XS measurable space, mu signed measure, E in S. Then mu plus of E can be defined as sup of mu F, F contained in E, F in S, and mu minus of E equals inf with a minus sign, mu of F, F contained in E, F in S. So these are, so you can define them independent of the Hahn decomposition. So this Hahn decomposition is not unique, but Jordan decomposition is unique. So proof, let X equals A union B Hahn decomposition. So EF in S and F contained in E. So mu plus mu of F intersection A is less than or equal to mu of E intersection A, because mu is a measure now on when intersected with A, mu is same as mu plus, and therefore mu of F intersection A will be less than or equal to mu of E intersection A by the monotonicity of a measure. Okay, and so you have mu F equal to mu of F intersection A plus mu of F intersection B, and this is of course negative, so this is less than equal to mu of F intersection A, which is less than equal to mu of E intersection A. Okay, and that is equal to mu plus of E, and this is true for all sets. Therefore sup of mu F, F contained in E, F in S, is of course less than equal to mu plus of E. But mu plus of E is mu of E intersection A, and E intersection A is contained in E, and therefore this is less than equal to sup mu F, F contained in E and F in S, trivially, and therefore this implies star. So in the same way, similarly, double star follows. So now example. So XS mu measure space and F integrable. Then you consider nu of E, the sign measure, which is integral over E F d mu E in S. Then Hahn decomposition. A will be set of all x in X such that Fx, F plus of x is greater than 0, and B equals set of all x in X such that F minus of x is greater or equal to 0. You can put the equality sign in either one, since we have already seen Hahn decomposition is not unique. So this gives you a Hahn decomposition, because this is a positive set, because if you integrate anything in on a subspace of this, then since F plus is positive, so F equals F plus, and therefore the integral will be positive, and so the measure will be positive. Similarly in B, the measure will be negative, because the F minus is so F equals F minus F minus, and therefore this will be true. Okay, so then the nu plus of E equals integral over E F plus d mu, and nu minus of E equals minus integral sorry, integral over E F minus d, and then mod nu of E equals integral over E mod F d mu, as you can easily see. Okay. So if X is a measurable space and mu is a sign measure, and F measurable real valued function on X, okay, then we can define So f integrable with respect to mod mu is the same as saying f integrable with respect to both mu plus and mu minus. Only then that integral will be finite. And then we can define the integral over x. So then you define, so if f is integrable with respect to the sign measure, so then we say f is integrable with respect to mu, which is now a sign measure, and you define integral x f d mu as is integral over x f d mu plus minus integral over x f d mu minus, where mu equals mu plus minus mu minus Jordan. So if mu is a complex measure, we say f is integrable with respect to mu if and only if f integrable with respect to mu1 and mu2, where mu equals mu1 plus I mu2. Now mu1, mu2 are sign measures, and you say integral of f d mu over x is equal to integral of f d mu1 over x plus I times integral of f d mu2 over x. So mu1, mu2 signed measures. And then so we know how to integrate with respect to sign measure, and so if it is integrable with respect to both of them, then you say you can define the measure. Okay, so these are about integral. So now we come to a different notion. So this is the notion of absolute continuity. We already encountered absolutely continuous of one measure with respect to another, and we said that integral, if you have nu e equals integral f d mu over e, where mu is a measure, then we say that measure was absolutely continuous. So now we make precise this definition. So definition, so XS measurable spaces, space, mu and nu sign measures. So we say that nu is absolutely continuous with respect to mu, and the symbol is nu less than mu. Okay, and if nu e equal to 0, whenever mod mu e equal to 0, E in S. So if mod mu e vanishes, then nu e should also vanish. Okay, so example, XS mu measure space. So this is the example we've already seen. F integrable and nu e equals integral over E f d mu. And since mu is a measure, mod mu measure implies mod mu is the same as mu. It has no lower variation, so there's no need for the whole set is a positive set, and therefore nu e. So this is clear. So nu is absolutely continuous with respect to mu. example, XS measurable space and mu new measures. That means they are positive. Okay, then mu is obviously absolutely continuous with respect to mu plus nu, because if mu plus nu is 0, then both mu e and nu e are 0, and consequently you also have nu is absolutely continuous with respect to mu plus nu. Then example again, XS measurable space, mu signed measure. So mu equals mu plus minus mu minus, job done, decomposition. And then you have mu plus is absolutely continuous with respect to mu, mu minus is absolutely continuous with respect to mu, because you have, and you also have trivially, mu is absolutely continuous with respect to mod mu, because if mod mu is 0, then mu plus is 0, mu minus is 0, and therefore mu is also 0. So all these things are obvious trivial examples. So now it's slightly different example, which is tells you more about this definition. So x equals 0, 1, Lebesgue measure. Take f equal to the set 0, half, and then you define f1x equals 2 chi of fx minus 1. So this means this will be plus 1, this is half, this is 0, 1, and this will be plus 1 here and minus 1 here. Okay, so this is plus 1, this is minus 1, and that is this function f1. And you have f2 of x equal to x, so this is x in x. So if E is a Lebesgue measurable set, then you define mu I of E equals integral over E fi d mu I equals 1 to. Now mod f1 is identically equal to 1, so this means mod mu 1 is the same as the Lebesgue measure L1. So this implies, so sorry, this is dm1. Okay. And therefore this implies that mu2 is absolutely continuous with respect to mu1, because f1 is mod mu1 is just m1, and therefore this is with respect to that, and we now know that mu2 of E is equal to integral f2 dm1, and therefore you have that mu2 is absolutely continuous with it. But mu1 of x is integral f1 dm1, and that is 0, and mu2 of x equals integral 0 to 1 x dx, because it's a continuous function, and that's equal to 1/2, which is not equal to 0. So mu1 of E equal to 0 does not imply mu2 of E equal to 0. Okay, so when you have absolute continuity, it is only mod which matters, not the function itself. So that is this example you have here. Now proposition XS measurable space, mu and nu signed measures. The following are equivalent. 1, nu is absolutely continuous with respect to mu plus minus, absolutely continuous with respect to mu, and then 3, mod nu absolutely continuous with respect to mod mu. So any one of these, so proof 1 implies 2. So X equals A union B, Hahn decomposition for nu. So E in S, so nu plus of E equals nu of E intersection A, and nu minus of E equals minus nu of E intersection B. So if mod mu E equal to 0, then 0 is less than equal to mod mu E intersection A, which is less than equal to mod mu. It's a measure, so it's monotone, and that is 0, and therefore this is equal to 0. Okay, and zero less than equal to mod mu E intersection B, less than equal to mod mu of E equal to 0. So you have that if mod mu of E is 0, then mod mu of E intersection A, mod mu of E intersection B equal to 0, and therefore since nu is absolutely continuous with respect to mu, this means that nu plus of E intersection A equals nu minus of E intersection which is equal to nu of E intersection A equal to 0, and nu minus of E equals minus nu E intersection A B, and that's also equal to 0. And this implies that nu plus minus is absolutely continuous with respect to mu. Two implies 3. So if nu plus minus are absolutely with respect to mu, so mod mu of E equal to 0. So this implies nu plus of E equals nu minus of E equal to 0. This implies that mod nu of E equal to 0, and therefore mod nu is absolutely continuous with respect to mu. And then 3 implies 1. So mod mu of E equal to 0 implies mod nu of E equal to 0, and that implies that nu plus of E equals nu minus of E equal to 0. That means nu of E is 0, and therefore you have that nu is. So this completes the proof. Okay, so we will continue with the absolute continuity next time.